All right, so example 5 here, we have u not in component form. We have it expressed in terms of the unit vectors I and j, and v is the same way. We need to find 2u minus 3v. Now, there are a couple of different ways that you can do it, but the easiest way to do it is to just distribute and combine like terms. Okay, distribute and combine like terms. So we've got 2 times u, so just multiply 2 times the expression there for u, negative 3i plus 8j, minus 3 times v was 2i minus j. We're just going to distribute those scalars. We get negative 6i plus 16j minus 6i plus 3j. And we distribute the negative 3. And then we simply combine like terms. Negative 12i plus 19j. That's all that we're doing there. Multiplying the scalars, doing the combination by combining like terms. Now, if you were asked for the component form from there, let's just go ahead and talk about that real quick. That would just be negative 12, 19. You just pull the numbers out and make sure they're in the right order if they want the component form. All right, let's do another one. Example B, we've got 5 times u this time, so 5 times I minus 2j minus 2 times v, negative 3i plus 2j. Distribute the 5, 5i minus 10j, distribute the negative 2, positive 6i minus 4j, combine like terms, 11i minus 14j. So that's in unit vector form. In component form, that would be 11, negative 14. Since we're getting ready to talk about direction, let's go back to example A and talk about what quadrant that vector is in. It has a negative x component and a positive y component, so that's going to be in quadrant 2. Okay, that's in quadrant 2. I mentioned that because we're getting ready to do direction. Direction has to do with angles. It's very important to know what quadrant you're in when you're dealing with angles. In example B, we have a positive x and a negative y, so we are in quadrant 4 with that vector. Okay, go ahead and do the practice problem there. Should have gotten 13i minus 3j, so in component form that's 13, negative 3, so that one would also be in quadrant 4. Any questions there? Okay, so let's look at what if we have to break these down and find the components. So just as a reminder, I is the x component, j is the y component. Now I have an expression there. We'll talk about why it is the way that it is here in just a second by building from a right triangle. So you see the diagram that I've got there. That is representing vector v. Okay, we're going to label that vector there with its magnitude because that is what magnitude's the length. That segment there is the magnitude of vector v. If we break this down, though, into a right triangle, if we throw a segment there from the terminal point of our vector directly down to the horizontal axis, we have created a right angle, so we have a right triangle. So we've got the x component here, this is I on the horizontal, this is j on the vertical, our y component. If our angle is down here with the x-axis, where it should be, where it always is, if we were to set up our trig ratios, our x component is the adjacent side to our angle. So if we know the magnitude and the angle, and we want the x component, the adjacent and the hypotenuse is cosine. So that is where that expression right there, I is equal to the magnitude times cosine of the angle. That's why that is the way it is. J would be the opposite side, so opposite and hypotenuse is sine. So that is why the y component has sine in it. Now this is very convenient because think back to unit circle. I'm going to relate it all back to the beginning of our trig unit. The x coordinate was the value of cosine. The y coordinate was the value of sine. Now the reason for that is the same reasoning that we're using right here because of the adjacent and the opposite where they are at, but it goes hand in hand. You're used to x being cosine, y being sine, so it fits right in to what we're used to. Our angle, tangent of theta, is equal to j over I, y over x. Okay, j over I is just in terms of our vectors. You're used to y over x. So if we need to solve for the angle, say we have the components and we need to solve for the angle, then theta is equal to the inverse tangent of j over I. Okay, remember to solve for an angle, you use the inverse trig, so inverse tangent of j over I is going to give us our angle. So let's use that right here. Find the direction angle. Our vector is defined as 3i plus 3j. So if we set this up, tangent of theta is equal to the j component over the I component, 3 over 3. Now, I'm not going to use my calculator on this one. 3 over 3 is equal to 1. Is tangent equal to 1? Is that a special value? Is it a value that we can get off the unit circle? Yeah. Tangent's equal to 1 is where sine's equal to cosine, which happens at 45 degrees. Check and make sure that that makes sense. Positive x component, positive y component, so we're in quadrant 1. 45 degrees is in quadrant 1. Now, there is nothing stopping you from doing that in the calculator. As long as you're in degree mode, you can do the inverse tangent of 1, and you're going to get 45. Okay, I just wanted to take the opportunity to review something from our unit circle really quick. All right, let's do another one that's not on the unit circle. Okay, if our vector is 3i minus 4j, set it up. Tangent of theta is equal to the j component over the I component. Before we go any further, let's identify what quadrant we're in. Positive x, negative y. We are in quadrant 4. Okay, so theta is equal to the inverse tangent of negative 4 over 3. Negative 4 over 3 is not on our unit circle. Now, that does not mean that it doesn't exist. It's just not something convenient for us to find. Okay, so inverse tangent of negative 4 over 3 gives us negative 53.13 degrees. We don't want a negative answer. I am going to write that down, but that's not where we want to stay. Now, that is in the correct quadrant. Negative 53 degrees is in quadrant 4, but we would rather have the positive version of it, so we add 360. and we get